Welcome everyone, this is the first sub-module of 3 in Applications, Objectives and Limitations, which is the first topic to be covered on horizontal drilling, extended reach, geosteering and multilateral well course from Next Training. Due to the length of this module, we will break it into 3. By the end of the first sub-module, you will be able to define what directional drilling is, identify the key applications for directional drilling and understand different well profiles. Directional drilling is the controlled deviation of a well bore to reach a target that is not directly beneath the rig. This technology enhances reservoir access, improves production, and minimizes environmental impact. It is the science of deviating a well bore along a planned course to a subsurface target whose location is a given lateral distance, depth, and direction from the surface. In the picture, you can see 3 key components. This is the vertical depth, the lateral distance or displacement, and the direction of the well path from the rig to the target. The distance along the well bore is called the measured depth. Initially, directional drilling was used for 3 main applications. The first was sidetracking to bypass obstacles. In the absence of survey tools, this was done blind. A simple kick-off method would be either from a whipstock or cement plug. The next application is a directional relief well, which was drilled to intersect a well that is blowing out and enabling kill mud to be pumped. Initially, the relief wells would be drilled vertically adjacent to the target well, and then a whipstock would be run orientated to the direction of the target well. Later, electromagnetic range-finding technology was introduced to enable better identification of the direction and distance to intersect the target well. The third application was to drill into adjacent oil reservoirs illicitly. This practice can be common today, especially when oil fields are close to state lines or sovereign borders. Now, let's look at the most common well profiles. The oil industry began by drilling simple vertical wells, as seen in the left picture, which was the least technologically challenging at the time. As needs arose, when it became impossible to position wells directly above the reservoir which they wished to drill into, the slant well evolved. The slant, or J-shaped well, is probably the easiest of all directional wells to execute. Next, S-shaped wells, which are drilled explicitly as a slant well to a tangent inclination and then dropped back to vertical. The purpose of this is to enter the reservoir, usually a gas reservoir, in the best condition to cement the casing string. This is because gas can compromise cement while it is setting. Today, with more modern technology, the industry now has gas-blocking additives for cement slurries, providing great results at all inclinations. Finally, on the right, we have the horizontal profile. This profile is achievable due to the advances in directional drilling and the ability to run drill pipe in compression. The horizontal well evolved to meet the need for developing thin bed reservoirs. Let's now look at these in more detail. Vertical wells were and still are the most common type of well. The reservoirs for this application tend to be shallow and vast lakes of trapped oil. Therefore, the amount of power required to drill is low and the technology to drill is simple. The wells can be drilled very quickly, and many wells can be drilled to maximize oil recovery. Usually only small rigs are needed for this application, and they are often small enough to be truck mounted for ease of rig movement. Next are slant or J-type wells. As mentioned, these types of wells are common where the rig position cannot be placed directly above the reservoir. This can be for many reasons, including terrain, infrastructure, or environmental reasons. Initially, these wells could be drilled with simple tools, drilling vertically to a kickoff point and then using directional technology to build in the desired inclination before holding a tangent to the reservoir. Next, we have S-wells. These were the most demanding of the early directional wells. The drop sections can be challenging to achieve, mainly because dropping to vertical can also cause weight transfer, shock and vibration issues. These are common profiles when drilling gas wells. This is because during the cementing phase, it is essential that the cement is not compromised by gas ingress while setting. Drilling vertically into the reservoir minimizes this risk. However, this is limited today due to gas-blocking additives that can be added to the cement to prevent gas ingress. Finally, we have horizontal wells. This was a later development in directional well design due to the increased complexity and the need for more modern directional drilling technology to unlock the potential. The drilling of horizontal wells was initially developed to access thin reservoir layers such as fluvial-type plays. The application expanded into offshore wells, which were often limited by the available slots on the platform. By drilling horizontally in the reservoir, greater exposure could be achieved without requiring more wells, thus maximizing the available slots. As the industry matures, the need to access reserves that are difficult to access is becoming more possible as directional technology advances. A reason for this would be, for example, environmental. Below is a picture of Poole Harbour, which is located in Dorset, UK. Under this waterway is the Sherwood Reservoir, which is the largest onshore oil field in Western Europe. This area, however, is a UNESCO World Heritage Site and therefore had significant constraints on its development. Finally, it was decided to access the reservoir from a land location called Wytch Farm, which is in a forest. The field was initially discovered and developed by BP and, at the time, held the record as the longest extended reach well in the world. This development occurred during the transition to rotary steerable technology, which was a step change in lateral displacements that could be achieved. The photograph to the right shows the Thumb Islands that were built in 1965 to tap the East Wilmington oil field, located in Long Beach and San Pedro Bay, California. The islands were built to blend in with the coastal scenery, featuring landscaping and sound barriers to reduce the noise and visual impact of oil operations. When exploiting a reservoir offshore, it is very often financially advisable to build a large single platform or structure from which to drill the wells, as this will be more economical than building multiple small platforms over the same area. Onshore, with the concern for environmental impact, it has been seen more recently that instead of wells drilled vertically into the reservoir, the pad system has been adopted, where all the wellheads are gathered together in one small geographic location to minimize environmental impact. There's an additional advantage in that during the production life of the wells, maintenance and observation of production can be more efficient. Also, a significant reduction in the risk associated with road travel can be made. The two pictures on the right show salt diapirs, which form due to the buoyant behavior of salt in response to overlying sedimentary layers. This process is driven by several geological factors and principles. As the salt ascends, it can pierce through overlying sedimentary layers, forming a diapir. This process can create dome-like structures on the Earth's surface and is often associated with the formation of traps for hydrocarbons, making salt diapirs significant in the context of oil and gas exploration. Salt diapirs can also impact the local geology, influencing the structure and stratigraphy of the surrounding rock. Multilateral wells that exploit vastly diverse reservoirs, as shown in this graphic, are pretty rare in the industry. Most multilaterals are designed to exploit one or two sands within a major reservoir, and thus to blend two different API weights of crude into something that is produced at optimal rates. The other purpose of multilateral wells is to get maximum utilization from the production string, where the main bore on completion is determined to be capable of producing more than the exposed formation will yield. On the right is a picture showing steam-assisted gravity drainage, SAGD. This is an enhanced oil recovery technology for producing heavy crude oil and bitumen. It is a form of steam stimulation in which a pair of horizontal wells is drilled into the oil reservoir, one a few meters above the other. One horizontal well is used to pump the steam into the reservoir, and the other well is used to produce the oil. The Alberta Oil Sands is one of the largest and most common SAGD regions. In the Middle East, Kuwait and Oman utilize this technology to produce the oil. Coalbed methane CBM is a form of natural gas extracted from coal beds. In recent decades, it has become an important source of energy in the United States, Canada, Australia, and other countries. Where coal seams are thin or have low permeability, Horizontal wells are drilled. The coal is normally naturally saturated with water and the methane is trapped under pressure. The water is pumped out, reducing the pressure and allowing the methane to reabsorb from the coal surface. The methane gas flows through natural fractures or cleats in the coal and is collected through the well bore and sent to a separator. Vertical or horizontal fracturing of shales is a process used to develop unconventional wells. In normal reservoirs, the hydrocarbons have migrated from a source rock and are trapped by a cap rock or sealing layer. Unconventional drilling is where this source rock is developed. The source rock is a shale which has low permeability, preventing the hydrocarbons from being produced. After drilling the well, the rock is fractured under pressure to provide the permeability needed to allow the hydrocarbons to flow. The fracturing has a limited step out from the well bore. Therefore, to develop a field, many wells will need to be drilled, also to maximize the exposure of the formation to fracturing. Horizontal wells are common, resulting in many rows of wells drilled parallel through a reservoir. The most common unconventional fields are in the USA in the Permian Basin, Eagle Ford, and Bakken. Unconventional reservoirs are also common in Canada, Argentina, and China. Carbon sequestration is the process of capture and long-term storage of atmospheric carbon dioxide, CO2. Carbon sequestration describes the long-term storage of carbon dioxide or other forms of carbon to either mitigate or defer global warming and avoid dangerous climate change. It has been proposed as a way to slow the atmospheric and marine accumulation of greenhouse gases, which are released by burning fossil fuels, after initial high enthusiasm for carbon sequestration. It has been found that it is not really economically viable to remove carbon from the atmosphere or exhausts of carbon-burning power plants and store it in the subsurface when compared to other carbon-reducing technologies. Another application of this process is used in Europe, where instead of storing CO2, gas is stored. This is due to the high fluctuations in gas prices throughout the year. Buying and storing the gas when prices are low and then producing the gas when prices are high reduces the volatility of the gas to the consumers. The picture on the right shows how directional drilling is used to straddle rivers. Alright, we reached the end of this sub-module. Let's take a moment to review what we've covered and reflect on the key learning objectives. First, we look to explain what directional drilling is. That is, directional drilling is the science of deviating a wellbore along a planned course to a subsurface target whose location is a given lateral distance, depth, and direction from the surface. Then we explored the original applications of directional drilling. These were to deviate past an obstruction, drilling relief wells, and exploiting reserves from an adjacent concession. Next, we examined the typical well profiles used in directional drilling. The four key types are vertical, deviated or J-shape, S-curve, and horizontal wells. Each type serves different objectives based on reservoir geometry, cost, and surface constraints. We then moved on to the different modern applications. These included environmental, where we used ERD techniques for difficult to access resources, structural developments such as offshore platforms and pad drilling, production field developments such as multilaterals and SAGD, and unconventional reservoirs. Other applications can include gas storage and river crossings. This concludes the first sub-module on applications, objectives, and limitations. Thank you for listening. There should be a quiz to take as a recap, then progress. Please progress to the quiz.